Welcome back to the deep dive. Today we are cutting through the noise and diving headfirst into a fascinating single source that tackles a problem central to building truly intelligent agents.
Uh-huh.
How do you teach an AI model to collaborate with you, refining its output based on feedback over not just one but multiple steps?
Yeah, that iterative process is key.
Think about it like this. When you write code, it's rarely perfect on the first try. You compile, you run, you see errors, maybe tests fail,
Right, the classic loop.
and you use that feedback, that interaction, to iteratively improve the code. You go back and forth, turn after turn, until you get it right.
Mm-hmm.
This multi-turn refinement loop, especially using execution feedback, is incredibly natural for humans, but has been, well, a surprisingly tricky frontier for AI code generation models.
Absolutely. The current state of AI code generation often feels brittle
Mm.
in this regard. Many methods are essentially single shot.
Right, fire and forget.
Yeah, they take a prompt, generate code, and that's it. They have no mechanism to learn from or even use feedback from running that code. Then you have slightly more advanced techniques that might attempt a single correction based on an error message.
How like fixing one specific bug?
They can fix one specific issue.
Yeah.
But what happens when fixing one bug reveals another? Or when the initial feedback isn't a clear error, but just the code not quite doing what you intended, requiring subtle adjustments over several turns?
Which, as anyone who codes knows, is the vast majority of real-world debugging and refinement. It's a process.
Precisely. And while some approaches have attempted to tackle this multi-turn, feedback-driven process using powerful frameworks like reinforcement learning,
For sure.
they often run into significant scalability and training challenges. Reinforcement learning, while theoretically capable of optimizing for long-term goals across multiple steps, suffers from notorious problems like sparse rewards.
Ah, the reward problem.
Yeah, you often only get a clear signal like all tests passed at the very end of a long sequence of actions. This makes it hard to figure out which specific action several turns ago actually contributed to the final success.
That's the classic credit assignment problem. It's like winning a chess game after 50 moves and trying to isolate which single move halfway through was the game changer. It's incredibly difficult to attribute credit or blame efficiently.
Exactly. And training RL agents also typically requires massive amounts of exploration to discover successful sequences of actions in a potentially enormous state space.
Which is expensive?
Very expensive computationally and can be unstable. So we're left with this challenge. How do you capture that human-like, iterative, feedback-driven refinement process in AI code generation without getting tangled up in the complexity and inefficiency of traditional multi-step RL training?
And that brings us to our source for today's deep dive. We're digging into a research paper titled Multi-Turn Code Generation Through Single-Step Rewards by authors including Arnav Kumar Jain and Gonzalo Gonzalez Pumariega.
This paper introduces a novel approach they call µCODE.
Code? Like microcode, perhaps, suggesting something foundational or efficient.
The name is intriguing, yeah. And as we'll see, the approach aims for simplicity and scalability, so micro or fundamental might be fitting interpretations.
Okay, let's unpack this. Our mission in this deep dive is to understand what makes code different. What's the core technical insight that allows them to train for multi-turn generation without falling into that RL trap?
Right.
How is their algorithm structured? What are the key components and how do they work together? And critically, what do their experiments tell us about whether this approach actually works and why?
And what are the big takeaways?
Exactly. What are the essential technical takeaways for anyone thinking about building the next generation of code generation agents that can truly learn and refine?
Let's really hone in on the problem first to set the stage. As we discussed, the human process involves writing code, executing it, getting feedback errors, test failures, unexpected output,
The whole cycle.
and then iteratively modifying the code based on that feedback. Machine code generation methods have aspired to replicate this, especially the repair or refinement part.
Right. It's not just about generating code once. It's about generating code that works and being able to fix it when it doesn't.
And the paper points out the limitations of relying purely on prompting for this repair process.
Just telling the model, fix this error.
Yeah. While you can feed the model the error message and the code and ask it to fix it, this relies heavily on the model's pre-existing knowledge and the limited context window. You can't prompt your way out of every possible error state or teach complex multi-step recovery sequences solely through prompting. The model might offer a plausible fix, but it's often a guess based on patterns, not a truly learned repair policy derived from iterative interaction.
And the existing training paradigms struggle with the iterative part, you said.
Exactly. Current training methods are often geared towards single-turn success. They might train models to generate a complete solution from a prompt, but they don't train them to use feedback.
Or just one feedback step.
Or, yeah, they might train a model specifically for single-step correction, giving it a broken piece of code and an error, and asking for one fixed version. This works for isolated errors, but it fundamentally fails when the problem requires a sequence of refinements. The model isn't trained to generate code in turn 2 differently because of what happened in turn 1.
And this is where the multi-turn aspect using RL comes in, the methods that try to optimize across sequences.
Yes, and that's where the complexity hits. To train a model using traditional RL to optimize for passing tests after an arbitrary number of turns requires defining states, actions, transition dynamics, and a reward function over a multi-step process.
It gets complicated fast.
Very. The state includes the history of attempts and feedback. The actions are generating new code. The reward, passing tests, is often sparse and delivered way down the sequence.
Right, the delayed reward.
Learning in this setting means credit assignment over many steps, dealing with potentially enormous state and action spaces, and figuring out how to explore effectively to find successful paths. It's computationally very demanding and often unstable, requiring complex techniques like value function estimation or policy gradient methods that are notoriously difficult to get right in high-dimensional spaces like code generation.
So traditional RL, while powerful in theory, is kind of a heavy hammer for this specific problem, burdened by its generality. How does code propose a lighter, more effective approach?
Okay, this brings us to the core technical breakthrough presented in the paper. The authors propose that multi-turn code generation, despite looking like a complex sequential decision problem,
Right, it seems sequential.
actually possesses a specific structural property that fundamentally simplifies the learning challenge. They model it as what they call a one-step recoverable Markov decision process, or a one-step recoverable MDP.
A one-step recoverable MDP. That sounds very precise. Let's break that down. What does that mean in the practical context of writing and fixing code?
Okay, this is the key insight. It means that from any intermediate state you might find yourself in during the multi-turn process, any state defined by the original prompt and the history of previous code attempts and the feedback you received.
So even if my code is a mess after a few tries.
Right. From that state, the correct code solution for the original problem can, in principle, be reached in a single step or single turn.
Wait, hang on. So even if my code is completely broken after 3 turns of trying things, the correct code for the original problem is just one generator call away. That seems to contradict the need for multi-turns.
This is the subtle but critical point. The one step refers to generating the complete, correct final solution for the problem, not necessarily generating a minimal edit on the previous incorrect code.
Ah, okay.
The optimal action at any turn, from any state, which includes the history, is to generate the full, correct code snippet that satisfies the original prompt.
I see.
The history of previous attempts and feedback is crucial because it informs the model about what didn't work and why, guiding it towards generating the correct solution now. It helps the model condition its generation on the failures of the past.
Ah, I see. So the state includes the history, and the model needs to use that history to guide its generation. But the optimal outcome from that state isn't some complex sequence of edits.
No.
It's the generation of the single correct final code. And importantly, the definition of correct code is tied to the original prompt, not some intermediate goal derived from the error history.
Exactly. The optimality of a generated code solution is determined by whether it passes the test defined by the original problem description. This correctness is independent of the specific sequence of erroneous attempts that led to the current state.
Okay.
This is what makes the MDP one-step recoverable from any state. The optimal action, generating the correct final code, takes you directly to the goal, passing tests defined relative to the initial problem.
Okay, so the core idea is that the optimal policy at any point is just to generate the globally correct code. And the history helps you condition that generation to avoid past mistakes. What's the significance of framing it this way? Why is that important?
The significance is immense because it simplifies the learning problem dramatically. If the optimal solution is always reachable in a single step from any state, you don't need to train a complex policy to optimize a long-term cumulative reward over many turns.
Right, no need for that complex look ahead.
You can effectively train the model to maximize a one-step reward. The immediate correctness of the code generated in the current turn relative to the original problem.
So instead of trying to learn a multi-step strategy in a vast state action space using complex RL, you can reduce it to learning to generate the right code at each step, guided by history.
Precisely. This transforms the problem from complex, unstable reinforcement learning with its exploration burden and difficult credit assignment into something much closer to interactive imitation learning.
Imitation learning. Okay.
The model learns to imitate the optimal behavior generating correct code using data collected through interaction, rollouts, and feedback. This imitation learning approach is far more stable and computationally efficient than typical RL for this specific task structure.
And the expert it's imitating.
The expert you're imitating is essentially the policy that generates the correct code for the problem, and you can approximate its quality for any candidate solution using an oracle, or as code does, a learned approximation.
That insight feels genuinely powerful. If you can identify this one-step recoverable property, you can sidestep a lot of the complexity that makes multi-step RL so difficult in general. It's really exploiting a structural property of the problem domain.
It is.
So how do they translate this insight into a concrete training algorithm? What does code actually do?
The paper presents code as a simple and scalable implementation of this idea. It follows an expert iteration framework.
Expert iteration.
Yeah, it's a class of algorithms where a learned policy iteratively improves by learning from an expert policy, which itself might be refined over time. In CODE's case, the expert policy is defined and guided by a learned component, a verifier.
Okay, expert iteration using a learned generator and a learned verifier. Got it.
That's right. The two main components are a learned generator, denoted as PO, which produces the code,
The code writer.
and a learned verifier, denoted as RAW, which evaluates the quality of code solutions.
The code judge.
Basically, yeah.
Walk me through the iterative training loop they describe in algorithm 1. How do these two components learn together? How does this dance work?
Okay, let's unpack algorithm 1 step by step. The training proceeds in iterations, in each iteration. First, you perform a rollout.
Okay, run the model.
You take the current version of your generator and use it to interact with the environment, meaning you give it coding problems, let it generate solutions over multiple turns, and collect the execution feedback, like error messages or test results.
Like simulating a developer trying things out?
Exactly. This process, which they detail further in algorithm 2, the inference process, also used for rollouts, essentially simulates the multi-turn code generation and feedback loop. During these rollouts, you're capturing the prompt, the history of attempts and feedback for each turn, the code generated at that turn, and the final outcome, like whether the code passed tests on the first try it got right.
So you're using your current generator to explore the problem space and gather concrete examples of what happens when it tries to solve problems over turns, including its successes and failures, getting real data.
Precisely. This new data collected in the current iteration, let's call it DI, is then added to a growing aggregate dataset, D, which accumulates data across all training iterations.
Building up a library of attempts.
Right. Next, you train the verifier. You take this entire aggregated dataset, D, and train the learned verifier on it.
Using all the data collected so far?
Yep. The verifier is trained to score candidate code snippets for a given problem prompt. Essentially, it learns to predict how likely a piece of code is to be correct based on the prompt and the code itself.
It's learning to be a judge of code quality, using the success-failure labels from the rollouts as ground truth, learning what good code looks like for that problem.
Exactly. Once the verifier is updated, you construct the expert. This is where the verifier becomes central to defining the expert policy.
Okay, how?
For each prompt in your aggregated dataset, D, you define the optimal solution, let's call it YI, as the code snippet already present in that dataset that receives the highest score from your learned verifier.
So not necessarily the absolute perfect solution,
Not necessarily.
but the best solution discovered so far by the generator and valued highest by the current verifier. It's essentially a local search within the collected data guided by the learned verifier.
Exactly. It's a bootstrapping mechanism. The verifier is used to identify the most promising attempts that the generator has already produced.
Okay, makes sense. Then what?
Then you relabel data. You take the collected data and create a new dataset, the expert dataset, D. For each state, prompt plus history, in your data, you pair it with the E that you just identified using the verifier-guided local search.
So the new training data for the generator looks like, given this problem and this history of attempts and feedback, you should have produced this code, IA, because our verifier says it's the best candidate we've seen so far.
That's the idea. You're creating target outputs for the generator based on the verifier's judgment of the best available code from the rollouts.
Got it. And the last step.
Finally, you train the generator. The generator pick is fine-tuned on this relabeled expert dataset, DU. It learns to produce the code solutions that the verifier-guided expert identified as the best attempts, conditioned on the corresponding prompt and history.
And this loop repeats. You roll out, update the verifier on the new data, use the improved verifier to find better expert examples in the dataset, and then train the generator to produce those better examples.
Precisely. With each iteration, the generator gets better at producing promising code, leading to richer data collection in the rollouts.
Okay.
The verifier trains on this expanded, higher quality data, becoming a more accurate judge of code quality.
Right.
This improved verifier then guides the identification of potentially even better Yi candidates in the dataset, providing a stronger training signal for the generator in the next iteration. It's a powerful, positive feedback loop where the generator and verifier bootstrap each other towards better performance.
That iterative process makes sense. It's like the generator explores, the verifier evaluates those explorations, and then the generator learns from the evaluations to explore more effectively next time. Let's drill down a bit into the training of the individual components, starting with the learned verifier. You mentioned it provides depth scores.
Yes, the learned verifier is a critical piece. Its main roles are providing those dense scalar scores for code solutions.
Dense meaning like a range, not just 0 or 1.
Exactly. A spectrum of scores, not just binary pass-fail. These scores are used both to guide the expert construction during training, finding that Yi, and later during inference for selecting the best candidate in the multi-turn best of n search. Unlike the binary oracle reward, 1 for pass, 0 for fail, the verifier gives a score that can, in principle, differentiate between two incorrect solutions, indicating which one is more correct or more promising.
Providing a richer signal.
Much richer than sparse binary rewards.
What makes its training different or advantageous compared to how, say, process reward functions might be trained in a generic RL setup?
The paper highlights two key points. First, the verifier is conditioned only on the initial prompt and the current code solution being evaluated. It doesn't need the entire, potentially long and complex sequence of previous attempts and feedback to give a score.
So its judgment of a piece of code is independent of the specific path taken to arrive at that code. Simpler input.
Right. And second, and perhaps most crucially, it's trained via standard supervised learning. You treat the oracle reward, pass-fail on tests, as the ground truth label for the code snippets collected during rollouts.
Supervised learning. That's definitely simpler to manage than many RL training schemes.
Much more stable and data efficient compared to many methods for training reward models or critics within complex RL pipelines, which often rely on, bootstrapped estimates or tricky off-policy data.
What specific loss functions did they use for training this verifier? Did they try different things?
They explored two primary loss functions. The first is the standard binary cross-entropy BCE loss.
Okay, the usual for binary classification.
Right. This treats the verifier training as a binary classification problem. Give it a code snippet and prompt, predict 1 if it passes the oracle tests, label as 1, and 0 if it fails, label as 0. It's the most straightforward way.
Makes sense. And the other?
The second is the Bradley-Terry BT loss. This loss function is inspired by work on training reward models from preferences, often seen in reinforcement learning from human feedback, RLHF.
Like preference tuning.
Exactly. Instead of training the verifier to predict an absolute binary outcome, you train to predict relative preferences. You sample pairs of code solutions from your dataset for the same prompt, one that passed tests my plus and one that failed, Y. The BT loss then trains the verifier to consistently score the correct solution, Y plus, higher than the incorrect one, Y.
So it learns this is better than that rather than this is absolutely good, bad. Training for relative ranking instead of absolute prediction. Why hypothesize that this might be better for the verifier?
Well, the intuition, supported by findings in training other types of reward models, is that learning to differentiate between better and worse solutions, the relative ranking might be an easier optimization problem than learning to predict the precise absolute outcome, binary pass-fail.
Especially with complex inputs like code.
Exactly. Especially when the input space is complex and the oracle signal can be noisy or sparse. The verifier's main job is to rank candidates during training, for identifying U, and inference for BON. So training it specifically for this relative ranking task seems well aligned with its purpose,
Focuses the learning on what matters for selection.
Right. It focuses the learning signal on the critical distinction between good and bad solutions, which is ultimately what the system needs to identify.
That makes a lot of sense. It's less about hitting a specific target value and more about just establishing the correct order. What about the generator? How is that trained in detail?
The generator's role, as we said, is to produce the code. As part of the multi-turn process, it's conditioned on the initial problem description and the accumulated history of previous attempts and the execution feedback received.
So it knows what happened before.
This is how it learns to leverage the feedback to refine its output in subsequent turns. Its training process, as we saw in Algorithm 1, is primarily fine-tuning on the expert dataset.
And just to reiterate, GA is constructed using the learned verifier. For each prompt and history state, D contains the best code solution found so far in the collected data for that prompt, as identified by the learned verifier.
Exactly. It's prompt history maps to U, where Y is essentially argmax C and D for that prompt Y. So training on D means the generator is learning a policy that, given a state, prompt plus history, is likely to generate the code snippet that the learned verifier deems best among all the attempts seen for that problem so far.
So the generator is learning to imitate the behavior of finding the best seen so far solution, with the verifier acting as the judge defining best.
Correct. This iterative training where the generator produces data, the verifier learns from that data, and then the generator learns from the verifier's judgment on that data creates that powerful bootstrapping effect we talked about.
Okay, so we understand the training process, the iterative dance between the generator and the learned verifier, guided by the one-step recoverable MDP insight. How do they use these trained models to actually solve a coding problem at inference time, when you actually want an answer?
Right. At inference time, the goal is to generate a high-quality code solution within a predefined budget, typically measured by the maximum number of turns, P, or maybe the total number of generator calls allowed. Code uses a strategy called multi-turn best of n, BON n.
We're familiar with standard best of n, where you generate n candidates and pick the best one somehow. How does that work in this multi-turn context? Is it just BON at each step?
Pretty much, but guided. Algorithm 2 details the inference process. It runs for up to t turns. At each turn, let's say turn t, starting with t1.
Okay.
The generator's call. It's conditioned on the current state, which includes the initial prompt and the history of all previous attempts and their execution feedback. It generates n candidate code solutions.
So at each turn, it tries n different things, informed by what's happened before, like parallel universes of fixes.
Kinda, yeah. Then here's where the learned verifier comes in. The learned verifier ARTS scores all n of these newly generated candidates based on the initial prompt. Remember, the verifier only needs the prompt and the code to score, not the full history.
Right, simpler input.
The candidate code solution with the highest score, according to the verifier, is selected as the chosen solution for that turn. Let's call it your key.
So the verifier is acting as the real-time guide, picking the most promising candidate out of the n generated at each step, not just picking randomly or the first one.
Exactly. This chosen solution, or your AT, is then executed on the public tests associated with the problem to get feedback.
Why run it on public tests if you have the verifier score? Isn't the verifier supposed to predict correctness?
Because the learned verifier is an approximation, it's not perfect. It's learned from data. A high verifier score is a good sign, but it doesn't guarantee correctness. The public tests provide a necessary ground truth check, albeit a potentially limited one.
Ah, okay. A reality check.
Right. If the selected solution, IE, passes the public tests, or if you've reached the maximum number of turns, T, the inference process stops. The first solution to pass public tests is considered the final output and is then evaluated on the hidden private tests.
And if it fails the public tests?
If it fails the public tests and you haven't hit the turn limit, the state is updated to include IE and the feedback from the public tests, and you proceed to the next turn, turn 10 plus 1.
This multi-turn bond feels very strategic. You're not just blindly exploring. You're using the verifier at each step to prune the possibilities down to the single most promising one, then getting real feedback and iterating.
Precisely. This selection step, guided by the verifier, is key. It keeps the search efficient. You only call the generator n times per turn, leading to a total of nt generated. It calls over t turns. That's a linear increase. Without such a guided selection mechanism, a multi-turn search over n candidates could potentially lead to an exponential explosion in possibilities you'd have to track.
Makes sense. Okay, we've covered the training and inference mechanics. Now let's return to the theory for a moment. How does that initial insight about the one-step recoverable MDP theoretically underpin why code is effective and efficient. Why does that structural assumption matter so much?
It all circles back to that fundamental structural property they identified. The fact that the optimal code solution for the original problem can be generated from any intermediate state in a single step,
Right.
and that the optimal policy, generating the correct code, doesn't depend on the complex path-dependent history of how you got to that state, but rather on leveraging the history to guide generation relative to the original goal. That's what makes their approach theoretically sound and efficient.
How does that specific structure enable interactive imitation learning so effectively compared to trying to do general RL?
Well, in general RL, you might need to explore many possible action sequences from each state to find the optimal path, which is, as we said, sample inefficient. But for a one-step recoverable MDP, the expert policy, the one that maximizes the one-step reward correctness, is conceptually simple.
Yeah.
It's just the policy that generates the correct code.
Doesn't need complex planning.
Exactly. You don't need complex value function estimation or multi-step backups to define the optimal action from any state. You just need to be able to generate the correct solution, potentially using the history to guide that generation. And crucially, the learned verifier provides an effective, trainable way to estimate the quality of candidate solutions relative to this one-step goal. It provides that dense signal that helps the system learn.
Okay.
Even if the generator produces a suboptimal solution at turn t, the theory suggests that from the resulting state at turn t+1, which includes the history of the mistake, the optimal action is still just generating the correct code for the original problem. The system can recover.
Ah, recoverability.
Because the goal and the path to it, a single generative step, are defined relative to the initial prompt, not dependent on a precise sequence of error fixes.
So the error doesn't put you on a fundamentally different complex trajectory. You're always just trying to hit the same target, the correct final code from wherever you are now,
Yeah.
using the history as clues, less getting lost.
Exactly. The paper even provides a theoretical guarantee. They cite a performance-bound theorem, Theorem 3.2 in the paper, which states that for a one-step recoverable MDP, code achieves a performance difference from the optimal policy bounded by OT times plus NF.
Okay, T is turns, N is candidates. What are epsilon and gamma?
T is the number of turns, horizon, is the realizability error, basically, how well the generator and verifier could approximate the true optimal policy or value function.
How good your learned models are.
Right, and relates to the average regret over the N candidates selected at each step.
That OT plus M bound. Can you help us understand the intuition there, especially regarding the dependency on T, the number of turns?
The key part is the OT dependency on the horizon T. This means that the error relative to the optimal policy scales linearly with the number of turns. Compare this to the OT bound you typically get for unrecoverable MDPs, where errors can compound quadratically over time.
Ah, so for unrecoverable problems, a small error at one step can lead to a much larger divergence from the optimal path over subsequent steps, quadratically increasing the total error. But for one-step recoverable problems like this, the error from one step doesn't compound as severely, it just adds linearly.
That's the intuition, exactly, because you can always recover by generating the correct solution in one go from any state. Mistakes don't put you exponentially off track. The theoretical guarantee confirms that exploiting this structure yields a much better performance bound regarding the horizon T.
The core theoretical takeaway, then, is that code works by recognizing and leveraging the specific one-step recoverable structure of the multi-turn code generation problem. This allows them to transform a difficult general RL problem into a more stable and efficient imitation learning task, providing strong theoretical guarantees that aren't available for general sequential decision problems.
Precisely.
And you said this insight about one-step recoverability could potentially apply to other AI tasks beyond code.
That's one of the exciting implications, yeah. The theoretical findings suggest that if we can identify other tasks in AI where the optimal action or solution is history independent and can be reached in a single step from any intermediate state, perhaps in certain types of multi-step reasoning, planning, or generation, then similar, more efficient learning paradigms exploiting this structure might be applicable.
Avoiding the need for complex general-purpose RL.
Exactly. It could be a powerful way to simplify training for certain classes of problems.
That's a profound point about analyzing task structure before throwing general learning algorithms at it. Really understand the problem first. All right, let's move from theory to practice. Did the experimental results actually validate this approach and the theoretical claims? What were they trying to test?
The experiments aim to answer a few key questions. How does code perform against existing state-of-the-art multi-turn methods? Does the learned verifier actually provide a significant benefit, both during training for relabeling and during inference for bond selection? And which loss function works best for training that verifier BCE or BT?
What was the experimental setup? Models, data?
They use Llama 3 instruct models as the base, specifically the 1 billion and 8 billion parameter variants. The datasets were MBPP, mostly basic Python problems, and human eval, both standard benchmarks for Python code generation.
Okay, standard setup.
They compared code against several baselines. Standard instruct models use greedily or with simple multi-turn prompting, star, which is a single-turn supervised fine-tuning method, and multi-star, a multi-turn variant of star trained on multi-turn data, but without code's learned verifier for guidance.
How did they measure success?
The evaluation metrics were standard best of n pass accuracy and greedy decoding accuracy, which is just bond with n1.
And that public-private test split.
Right, a crucial detail in their setup was the public-private test split strategy. For each problem, they designated only a small subset of tests, like maybe a single docstring example or one official test case as public.
The model gets to see the results from those.
Yes, the models could see and execute on those during the multi-turn process. The rest of the tests were private, used only for final evaluation after the model produced its final answer.
Why is that important?
It's important because it prevents models from simply overfitting to the public tests and ensures they actually learn to generate correct code that generalizes, much like real-world coding challenges where you only have limited examples to test against initially.
Good point. Okay, let's look at the main results in Table 1. How did code stack up against the baselines? Start with greedy, N1.
Okay, starting with the greedy results, N1. We see that methods incorporating multi-turn feedback, so instruct multi-turn, multi-star, and µCODE, generally outperform the single-turn methods like instruct greedy and star.
So feedback helps. No surprise there.
Right, it empirically confirms the value of using execution feedback. Crucially, even at N1, code outperforms multi-star, particularly on the 1B models. For example, on human eval 1B, code achieved 35.4% greedy accuracy compared to multi-star's 33.5%.
That's almost a 2% absolute gain.
Yeah, a 1.9% absolute gain.
Yeah.
This indicates that the generator, trained using the code approach with that learned verifier data, is inherently better at producing correct code even without the fancy bond search at inference.
The training itself made the generator better.
Exactly. The 8B models showed similar trends, though with some dataset variations, performance was closer sometimes.
And with Bond and 5, leveraging that multi-turn search guided by the verifier.
This is where code really shines and demonstrates the power of the learned verifier in action. First off, all methods saw gains with bond search compared to greedy decoding, which is expected. Sampling multiple options generally helps.
More shots on goal.
Right, but code itself shows substantial internal gains with bond, up to 12.8% absolute improvement over its own greedy performance on human eval 1B. That's a big jump just from using the bond search with its verifier.
Wow, okay.
And when comparing code plus bond against the baselines plus bond, code consistently outperforms them. On MBPP1B, code plus bond got 50.7% versus multi-star plus bond's 47.9%.
Another almost 3% gain.
Yeah, 2.8% gain. On human eval 1B, it was 41.7% versus 39.6%, a 2.1% gain. These numbers, while perhaps seemingly small in percentage points, represent solving significantly more problems correctly.
Definitely non-trivial gains on these benchmarks.
The results strongly support that the learned verifier, used both in training and for inference time selection, is key to code's performance boost in the multi-turn setting.
So the learned verifier is not just some helper during training, it's a critical component for performance at test time by effectively guiding the search for a correct solution over turns.
Exactly, and the ablation studies provide deeper insights into why this is the case, breaking down the contributions.
Let's dive into those ablations, starting with the verifier for relabeling analysis in Figure 2. How did using the learned verifier to identify the expert training examples compare to other methods, like using a perfect oracle?
Yeah, this is a very interesting finding, maybe even counterintuitive. You might think that using an oracle verifier, OV, a perfect check for whether a solution in your dataset is actually correct, would be the best way to identify expert data for training the generator.
Seems logical. Train on known good examples.
Right. However, Figure 2 shows that relabeling data using the learned verifier, LV, significantly outperforms relabeling using the naive oracle verifier, OV. And a combination, OV plus LV, which uses both, performs even better than just OV alone, but still LV is crucial.
Whoa, wait. Why would training the generator on data identified by an imperfect learned verifier be better than training it on data identified by a perfect oracle? That seems backward.
The hypothesis supported by these results is that the learned verifier provides a richer, more informative signal than the binary oracle. The oracle only tells you if a solution is perfectly correct, 1, or perfectly incorrect, 0.
Black and white.
Exactly. The learned verifier, even if imperfect, can assign a scalar score that captures nuances and might score partially correct solutions higher than completely nonsensical ones, or identify solutions that are close to correct even if they don't pass all tests. This smoother, denser signal from the LV likely provides a better gradient or target for the generator to learn from compared to the sparse binary signal from the OV.
Ah, so it's teaching the generator not just to hit the perfect bullseye, but how to get closer to the target, providing more useful intermediate guidance.
That's the idea. It seems that judging promise or relative correctness is a better training signal here than just judging absolute perfection.
That's a key technical takeaway right there. A well-trained, learned verifier is more than just an approximation of the oracle. It provides a qualitatively different, potentially more useful training signal for the generator in this iterative context. What about the generator's ability to improve over turns itself? Figure 3 analyze that.
Figure 3 is a direct look at the multi-turn capability learned by the generator. It shows the bond accuracy using whatever selection mechanism that method uses across multiple turns, turn 1, turn 2, turn 3.
What did it show?
For code, the bond accuracy consistently increases from turn 1 to turn 3, especially for N5. This demonstrates that code's generator, trained with that learned verifier feedback loop, becomes better at utilizing the execution feedback from previous turns to recover from errors and generate successful solutions in subsequent turns.
It's actually learning the interactive repair process.
It seems so. In contrast, baselines like multi-star show only marginal improvements across turns, suggesting their training doesn't effectively teach the generator how to leverage multi-turn feedback for recovery in the same way.
That's strong evidence that Cone training approach is successfully instilling that iterative improvement capability. Okay, what about the verifier's role at test time? Table 2 looked at different inference selection strategies within the bond framework.
Right. Table 2 compares various methods for selecting the single best solution out of the n candidates generated at each turn during inference they looked at. Random selection,
Just pick one.
selecting based purely on the learned verifier score,
Uh-huh.
LV, selecting based on passing the public tests, PT,
The ground truth check.
and a combination. First check public tests, then use the learned verifier score to break ties if needed, PT plus LV.
And the results.
As expected, any form of intelligent selection, LV, PT, PT plus LV, beats random by a lot. Using public tests, PT, is generally better than just using the learned verifier LV alone, which makes sense. PT is a form of ground truth feedback, even if limited.
Okay.
However, the combination strategy, PT plus LV, consistently performs the best across models and datasets.
The hybrid approach wins. Why?
It leverages the strengths of both. If a solution passes public tests, it's likely good, so you prioritize that. But if multiple solutions pass the public tests, or if all n candidates fail public tests in a given turn,
Which must happen often.
right, then the learned verifier's dense score is used to pick the most promising one among the passers, or the least bad one among the failers.
So the verifier isn't just a backup, it's adding value even when public tests are available. Why might that be? Why does the verifier help break ties or pick among failures?
The paper hypothesizes 2 reasons. First, the LV might help filter out incorrect solutions that accidentally pass the limited public tests but would fail private tests. The verifier, having seen more data during training, might detect subtle flaws that the few public tests miss.
Okay, a better sniff test.
Second, when all candidates fail public tests, the verifier helps select the least bad or most promising incorrect solution among the n options, providing a better, even if still wrong, starting point for the next turn's generation, based on the verifier's nuanced judgment.
Gives the generator better history to work with for recovery in the next turn.
Exactly.
Yeah.
It aligns with the multi-turn learning idea. Picking the best intermediate step based on a learned quality signal helps guide the overall trajectory towards success.
That makes sense. What about test time scaling with n in Figure 4? How many candidates per turn are needed? Does more always equal better?
Figure 4 shows the standard pattern you often see. Increasing n, the number of candidates generated per turn, improves bond accuracy, but with diminishing returns.
Flattens out.
Yeah. The performance gains start to plateau around n-5 to 7 in their experiments, suggesting that generating, say, 20 candidates per turn might offer little additional benefit over 7, but costs much more compute.
So a sweet spot around 5.7.
Seems like it for these tasks. But more critically, Figure 4 also compares the performance of the learned verifier itself when trained on different data. They compared a verifier trained on samples generated by the initial untrained base model, they label it base verifier, versus a verifier trained on samples generated by the iteratively improved code generator during its training rollouts, labeled code verifier.
Ah, training the verifier on data from the thing it's actually verifying. And the result.
The verifier trained on samples from the iteratively improving on-policy code generator performs significantly better when used for test time selection.
That's huge.
It's a crucial practical detail. The quality of your learned reward or verifier model depends heavily on the distribution of the data it's trained on. To effectively guide an improving policy, the generator, the verifier needs to see and learn from the kinds of samples the policy is currently generating.
You can't just train the verifier once on old data and expect it to work well with a much better generator later.
Right. Training the verifier on static data from an old policy, or even just the base model, is less effective. It reinforces the importance of that iterative training loop in algorithm 1, the generator and verifier improving together, with the verifier training data coming from the current generator's output.
Yeah.
It needs fresh, relevant data.
Very important point. Okay, finally, let's revisit the loss function for the verifier from Figure 5. Did the choice of BCE or BT loss make a difference in practice?
Yes, it did, quite clearly. Figure 5 consistently shows that the verifier trained using the Bradley-Terry BT loss significantly outperforms the verifier trained using standard binary cross-entropy, BCE, when both are used for test time bond selection.
So the preference-based loss wins.
It does. This holds true across data sets and increasing values of n.
That strongly supports their hypothesis that training the verifier for relative ranking, this code is better than that code, is more effective for its role in selection than training it for absolute binary prediction. This code will pass-fail tests.
Exactly. It validates the choice of drawing inspiration from preference-based reward modeling techniques like RLHF. Learning to differentiate better from worse samples seems to yield a more effective verifier for guiding the multi-turn search in this context.
Fascinating. They also included a qualitative example in Figure 6 to visually demonstrate the process. Can you walk us through that quickly? What does it show?
Sure. The example involves calculating the product of the unit digits of two integers. A simple problem, but good for illustration. It shows a multi-turn interaction. In turn 1, the generator produces several candidate solutions, I11, Y21, Y31, etc. The learned verifier scores them, and the one with the highest score is selected, let's say I11. This code Y11 is then executed on public tests, and in the example, it fails. The history is updated with I11 and the failure feedback.
Okay, attempt 1 failed.
In turn 2, the generator, now conditioned on this new history, produces a new batch of candidates, Y12, Y22, etc. The verifier scores these, and the top-scoring one, Y12, is selected. This code, Y12, is often an improvement based on the feedback from turn 1. Maybe it now attempts to handle string conversion correctly, but still has a bug.
Getting closer, maybe?
Right. It's executed and fails public tests again. History is updated again.
Still not there. Turn 3.
In turn 3, the generator tries again, conditioned on the history of 2 failed attempts. This time, among the candidates it produces, 2 might be completely correct solutions, example, Y13, Y23. The learned verifier evaluates these. Crucially, it assigns a high score to one or both of the correct solutions. One of the correct ones is chosen, say Y13. It passes public tests, and the process stops. It's then checked against private tests.
And you can see in the figure how the errors, often highlighted in yellow, are present in the initial attempts but diminish or disappear in the code selected by the verifier in later turns.
Exactly, in a clear visual trace, showing how the system, guided by the verifier's scoring and the execution feedback incorporated into the state history, iteratively refines its output over multiple turns until it converges on a correct solution. It demonstrates the learned multi-turn recovery process in action.
That ties all the pieces together nicely. Finally, let's briefly position code among related work to understand its novelty in the broader context. How does it compare to other approaches trying to solve similar problems?
The paper contrasts code with several existing types of methods. First, they distinguish it from pure prompting, or what they call agentic systems.
Like self-debugging, µCODE, things like that.
Exactly. Those like self-debugging, µCODE, AlphaCode, and µCODE rely on prompting a large language model to perform multi-step reasoning or correction. While these can show some improvement, they often yield limited gains compared to methods that are explicitly trained for the multi-turn process. Code is fundamentally a training approach, not just an inference time prompting strategy.
Got it. What else?
They also compare it to other methods that train critics or reward models like µCODE, Archer, and methods using Monte Carlo tree search like AlphaCode or MathShepherd. The key differentiator for code here is that core one-step recoverability insight.
Back to the MDP structure.
Right. This property allows code to use that simpler imitation learning framework in efficient data collection rollouts with one-step targets, compared to the more complex RL or MCTS algorithms required by methods that don't exploit this structural property. They mention µCODE is conceptually similar in training a critic, but wasn't designed for this specific multi-turn repair task, and Archer uses much more complex hierarchical RL.
So code is simply because of the problem structure assumption.
That's the claim. They also mention methods that don't learn critics but rely solely on sparse oracle rewards, like RLEF, PPO coder, highlighting that code's empirical results show the significant benefit of having a learned, dense reward signal from the verifier.
The verifier really matters.
And they differentiate from methods with a very limited number of turns, like score, which uses only 2 turns, or those that require a separate, potentially expensive, powerful LLM or oracle to explicitly generate correction steps, like rise. Code integrates the correction process directly into the generator's training via the relabeled data.
It really seems the central contribution is identifying that specific MDP structure for code generation, which then unlocks a more efficient learning paradigm compared to trying to apply generic, complex, multi-step learning methods.
That appears to be the crucial technical insight that underpins their approach and its observed effectiveness. Yeah.
Let's take a moment to mention the limitations the authors acknowledge in their paper. They were upfront about some things, right?
Yes, they are quite clear about these. First, the experimental evaluations were conducted using models up to 8 billion parameters.
Not the giant frontier models.
Right. While these are substantial models, it's an open question whether the same conclusions and performance gains would hold when scaling up to much larger models, like those with hundreds of billions or trillions of parameters. Scaling laws can sometimes introduce unexpected behaviors.
Fair point. What else?
Second, the training set for MBPP is relatively small, consisting of only 374 examples. The authors note that µCODE's performance on MBPP could potentially be further improved with a larger training dataset, which is a common finding in deep learning. More data usually helps.
Makes sense. And the last one.
And finally, their work focused exclusively on Python code generation. It's not guaranteed that the findings and the specific code implementation would directly generalize to other programming languages, Java, C++, key, JavaScript, etc.
Different syntax, different errors.
Exactly. Different syntax, semantics, testing environments, and common error types. Further research would be needed to confirm its applicability to other languages.
All fair points for future work. The paper also included an impact statement. What were the potential positive and negative impacts they discussed?
On the positive side, the potential impact is significant for streamlining software development. Automating the iterative process of writing, testing, and debugging code could substantially reduce the manual labor involved in routine coding tasks and accelerate development timelines.
Helping developers be more productive.
That's the hope. The acknowledged risk, however, is that, like any powerful automation tool, a system capable of generating and refining code at scale could potentially introduce and propagate subtle or complex bugs more quickly and broadly than human engineers might.
If it makes mistakes, it could make them fast and widespread.
Precisely. Ensuring robust quality control and validation processes will be critical as these tools become more widely adopted.
That risk highlights the importance of continued research not just on generating code, but on verifying its correctness and reliability.
Absolutely. Verification is key.
Okay. We have certainly taken a deep dive into code. We've understood the challenge of multi-turn code generation, why existing methods struggle, the core technical insight of modeling it as a one-step recoverable MDP, how the code algorithm iteratively trains a generator and learned verifier,
That bootstrapping dance.
how it performs multi-turn inference using best of n guided by that verifier, why it works theoretically with that improved performance bound, and what the extensive experimental results reveal about its effectiveness and the contribution of its components.
Including those interesting findings about learned verifier relabeling and the benefit of BT loss.
Right. So here's a final thought for you, our listeners, to consider directly from the implications of this research. The discovery that a seemingly complex sequential task like multi-turn code generation possesses a structural property being one-step recoverable in their formulation allows us to replace challenging sample and efficient reinforcement learning with a more stable and efficient imitation learning paradigm guided by a learned quality signal.
It's more than just a trick for code.
Exactly. It raises a broader question. What other complex multi-step reasoning, planning, or creative generation tasks that we currently view through the lens of general, difficult-to-train sequential decision processes might also possess a similar one-step recoverable or analogous simplifying structure?
Where else might this apply?
If we can identify these structures, could we unlock more efficient and scalable learning methods across diverse domains beyond code,
Hmm.
allowing us to build more capable and practical AI agents that learn effectively from iterative feedback and interaction?
It encourages us to look for inherent structure in complex problems, rather than just applying general-purpose algorithms off the shelf.
Indeed, a powerful reminder to analyze the task itself. Thanks for joining us for this deep dive. You can find links to the source material and more on our webpage. Until next time.